today we'll look at hybridization. The easiest explanation would be orbitals of different shapes and energies come together to form new orbitals. The second point that says number of orbitals joined would be equal to the new orbitals formed. Well, we'll look at this point when we start doing the hybridization, but for now just hold on to this second point. And also remember that let's say that I have sp3 orbital. This would mean that 4 orbitals are coming together. They're joining together, and 4 new orbitals are also getting formed. This is what this first point actually means. Similarly, if I have sp2, this means that 3 orbitals are coming together, they're joining, and also 3 orbitals are being produced. And in order to know if it's 3 orbitals or 4 orbitals, just look at the powers. That's what I do to make it easier for me. So let's say because p has a 2 on it, so assume that s has a 1 on it, so 2 plus 1 would be 3, so that's how it's 3 orbitals. And same goes for sp, which would be 2 orbitals. We'll look into it more after we try solving it. So let's say we are dealing with CH4. The first thing would be to check which is your central atom. So over here, I know carbon is my central atom because I have 4 hydrogens. So 4 hydrogens are gonna come together and join along with the carbon. So carbon is my central atom, so it's carbon 6. Second thing would be to do the electronic configuration, which would be 1s2, 2s2, 2p2 for carbon. Now I'll also open up the valence shell. So remember, my valence shell is 2s2, 2p2, not just 2p2. My whole all of the shell, all of the whole of the second shell would be my valence shell. So I'll open this up here. This is my, let me just write it like this. So this is my 2s, this is my 2p x, 2py, 2pz, 1 and 1. Now this is the ground state. I need to change it to its excited state. So that would be taking an electron from my 2s and shifting it to 2pz. So I'm left with 1 electron at 2s now. So at 2px, 2py, 2pz, each has 1 and 1 electron. Now the reason how I know that it needs to, so not every element needs to go into an excited state. So the reason why this one went was because there was a possibility that I could move my electron from my 2s to my 2pz. But let's say I had 2 electrons in my 2s, and my 2px, 2py, 2pz each has 1 electron. So now this is the most stable state. Well, it's not the most stable, but like if it's fully fulfilled, half fulfilled, or it's empty, those 3 states are like when it's the most stable, your the p orbital or even the d orbitals. So this is already stable, so I don't really need to change it to its excited state. However, over here in my example, I had an option to change it into its excited state. So that's why I moved my 1 electron to my 2pz electron. In this example, I cannot do that because this is already at its most stable state. It already is stable, so I don't really need to move an electron here to here. If I did, I would be actually, it would actually make it unstable. That is not what I want. So this is the excited state here. Now I can make the shapes of it. So let's say for 2s it would be a circle. Because the next are the p orbital, so p orbital is in a dumbbell shaped. And remember to put it into different axes because 2p, x, y, and z are in different axes. So 1, 1, and 1. This shows the electron. Now the next thing I need to do is combine them together. So this is what this second point was about. So it, well, not the second, the first point says that the orbitals of different energies, they come together to make new shapes. Over here, how is it different energies? Well, 2px, 2py, and 2pz they are degenerate orbitals. They are already at same energy level, but we're also combining 2s over here. So that's why we say that, oh, it's different energy. So we're combining them together to put them in same energies. So, and also combine them together to make one shape over here. So now the new shape would actually be something like this. It's not dumbbell, just remember that. Don't make it like a dumbbell shape, because that would cut out your marks. So each has one electron. Now how do I know I needed to make 4? Because I'm combining 4 shells, I know that I need to make 4 new shells. That is what this second point says. So if you're combining 4 shells together, you're making 4 new shells. Now how do I know what hybridization is it going under? Well, it would be sp3 over here. It's sp3 because I have 1 s orbital and 3 of my p orbitals. That's how it's sp3. So 3 orbitals of 3 p orbitals are coming together to do this. So this actually, so each of these orbitals would actually be sp3, 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 sp3. So in total I have 4 sp3 orbitals. So if you see over here, if it's going under sp3 hybridization, it would have 4 orbitals. sp2, that would mean 3 orbitals. sp would mean 2 orbitals. So in order to remember this thing also, just look at the power. So sp, and consider s as 1 power, so 3 plus 1 would be equal to 4, 2 plus 1 would equal 3, and 1 plus 1 equals 2. So this also tells you the number of orbitals you're producing. It's just a little trick that I use. Now I need to make the shape of sp4, sorry, not sp4, just CH4. So I have carbon here, carbon, and then because I'm using all of these 4 orbitals, I can just put it like this, this. Now this is my sp3, 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 sp3. Now I'll make a hydrogen here. Because hydrogen, the configuration for hydrogen is just 1s1, so it'll just have 1 electron in it. So this has 1, each has 1 electron, and then hydrogen also has 1 electron in it. So the next step is just combining all these together. So this step shows that they're approaching it. The hydrogen is approaching the carbon. In the next step, they're bonding together. So this and bond it together. So inside of it, it has 2 electrons now. Just combine together. And remember, so this is sp3, this is s. This is just s orbital. So this is sp3, 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 and this is it. NH3 as another example for hybridization. We'll look at the central atom, we'll determine that, which is nitrogen. We'll write down the electronic configuration for that, which is 2s2, 2p, 2p3. I'll open up my valence shell here. Two px, 2py, 2pz. Now for this is my ground state. I cannot write an excited state over here for this example because my p shell is already stable. It already has 1 electron in each of its shell. So if it was full-filled, half-filled, or empty, that makes it stable. So I can't really shift an electron from here to here. If, let's say, if I didn't have an electron over here, then I could possibly move 1 electron over here and then make it half filled and call it a state. But let's say I didn't have 2 electrons here. I already had 1 electron in my 2 and that was just in my 2px orbital. Am I supposed to move both of these electrons here and here? Well, that would be wrong. I can only move my 1 electron from my 2s orbital. So I would move 1 electron here and add it here, and then this would remove. But I cannot shift this over here because then my 2s orbital would be empty. But if we write down the electronic configuration, 2s is supposed to come before 2p. So I need to have 2s in order for 2p to be there. So I'll still have one electron over here. I cannot give the last electron that it has to my 2p shell. I can't do that. I can't do that. So, but for this example, this is half filled, so I'll just keep it like that. I'll draw my shapes here. So 2s is like this. This has a dumbbell shaped. Sorry. And this. I'll add my electrons in it. Now, how many shells for this question for NH3 would be hybridizing? We need to figure that out. So that actually means, like, would it be undergoing sp3 hybridization, sp2, or sp? So remember, if it's going under sp3, that means that 4 shells, 4 orbitals are combining together to produce 4 new shells. So that would mean that all of these shells are combining together. If it were sp2, that would mean that 2 p shells and 1 s shell are combining together. And if it were sp, that would mean 1 s shell and 1 p shell are combining together. But how do we figure out how many are combining for this one? Well, if we draw NH3, it's like this. So you might assume, like, oh, it's making 3 bonds. Remember, you need to figure out how many sigma bonds it's making in order to figure sigma bonds and lone pair it has. So it has 1 lone pair. So so over here I would know that I would assume my lone pair as 1. So 1 bond, 2, 3, and 4. So it has 4 bonds, so that would mean that it's going under sp3 hybridization. I do understand that I call this a bond, but just think of it as a bond. That would make more sense. Well, it doesn't because it's a lone pair, it's not a bond, but consider it as a bond. So it will mean, like, you will count this lone pair as 1, and then this bond is 1, this bond is 1, this bond is 1. So 4 bonds, and it's going under sp3. Now remember, let's say that it had another bond over here. Let's say this nitrogen was making 2 bonds with hydrogen over here. It doesn't, but let's just assume it for a second. Now, would you say that now this structure has 5 bonds? Would you assume that it's 5 bonds? So like 1, 2, 3, 4, and 5. So would you call it something like sp4? It doesn't exist, but you get it, right? Well, no, that would be wrong because you're only to assume the sigma bonds. So what's a sigma bond? Sigma bond is the first bond an atom makes with another atom. So where here, this is 1 sigma bond, this is another sigma bond, this is another sigma bond, because each of these bonds are made with another hydrogen. So 1 sigma bond, 2 sigma bond, and 3 sigma bond. However, if this nitrogen was making 2 bonds with this hydrogen, so this bond would be a sigma bond. We can also denote it like this, so sigma bond, and this bond would be a pi bond. So you can't consider a pi bond. You only to consider sigma bonds in order to figure out the hybridization. So for this example, it would be sp3. You also consider the lone pairs, that's why it's sp3. If you didn't consider the lone pairs, you would come to the conclusion that it is sp2, which would be wrong. You need to consider lone pairs as well. So sp3 here. So now that means that I have one of my 1s orbital is combining together, and then we have 3 of my p orbitals in question here. So I'll combine these together, and this would make a shape something like this. Now remember, this is not a dumbbell shape. This has 2 electrons, 1, 1, and 1. These 2 electrons are coming from here. Now I'll put my nitrogen in the center, and I'll put these around it. This is sp3, 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 sp3. In the next shape, I'll have the same, but Over here I'll show that my hydrogen is approaching it. Sorry, I don't have, oh wait, over here it doesn't have that. It's just no hydrogen would be over here because I only have 3 hydrogens. So it's like this. For the next part, I'll combine these 3 together. Don't forget the electrons too. So 1 electron, 1 electron, 1 electron. 1. This has 2 electrons. Over here, this has 2 electrons, and this would be 2 electrons, 2 electrons, and there is my structure. But one thing I need to add over here is that this is a tetrahedral structure. However, it's tetrahedral if I consider the electron pair geometry. But there's an other shape that I could take, which is the molecular geometry. If you consider the electron pair geometry, you would call this structure a tetrahedral structure. However, if you consider the molecular geometry, this would be trigonal pyramidal. And how would I show that one? Well, for that, I'll have nitrogen in the center. I'll have these bonds. I'll add my electrons in here. However, this bond that I had right here, this is actually a lone pair. So I'll just show this as a lone pair. And this would be my trigonal pyramidal geometry. But regardless of these 2 different kind of geometries, these both are sp3 hybridized. Now for tetrahedral, I'm considering all of this as a sigma bond. So I'll consider this as a sigma bond, this is a sigma bond, this is a sigma bond, and this is a sigma bond. However, for my molecular geometry, I consider sigma bonds and also my lone pair. So I need to point out which is a lone pair. So this was a lone pair, so I pointed that out as lone pair. The difference would be, well, because it's a tetrahedral, so the angle here would be 109.5 degrees. However, when it's a trigonal pyramidal, this angle would be 107 degrees. Now we'll look at hybridization for water. So we'll figure out the central atom, which is oxygen. We'll write down the electronic configuration for this. 2s2, 2p4. This is my valence shell. I'll open it up. Two S, 2p, 2py, 2pz. Now remember, I put 1 electron in each of these first because that's according to the Hund's law. So first you put you're supposed to put 1 electron, because this is a degenerate orbital, so you put 1 electron in each of these subshells, and then the rest use how many electrons are left, then you start with the first one again and start putting the rest of the electrons. So over here, because it was 4, I'm done with these 3, so now I can go back to my px and put the other electron over here. This is the ground state. Now over here, I cannot make an excited state over here because well, I do understand that this is not the most stable, but if we were to shift 1 electron over here, this would only put 1 electron over here and remove this electron from here. However, this does not make it stable. This doesn't make my p orbital stable. In order to do that, and then also, if you think that, oh, I can move this other electron here and then this would be stable, well, no, because this wouldn't exist. In order for this to work out, I need to have my s orbital over here, because if you look at it, the electronic configuration, it's 1s2 and then 2s2 and then 2p comes in. So 2p can't just exist like that. You need to have 2s. So, well, I mean, you can at least have 1 electron in it, but even if I were to use this 1 electron and add it over here, this still wouldn't become stable. So there's no point of even using that electron. So this just remains like this. However, let's say I did have 1 electron over here, and then I actually could use one like this electron from here and add it over here to make it stable, so I wouldn't have this one electron here. This would actually work because this is actually making my p orbital stable, and my 2s is also existing because it at least has one electron in it. But this is not the case for this question, so we'll just keep it over here. Now I'll draw my shapes. So 2s is a sphere, and the dumbbell shapes. I'll add my electrons in here. Now the question is, would it go under sp3, sp2, or sp hybridization? Well, if I look at water here, it has 2 lone pairs because I need to complete the octet rule over here, so it has 2 lone pairs. So how many would this be sp3 or not? Well, how many sigma bonds do we have here? We have 2 sigma bonds because this is 1 sigma bond, this is 2nd sigma bond. And how many lone pairs do we have? 1 lone pair, 2nd lone pair. So lone pair 2. So this would mean that we have sp3 hybridization. So that means 3 of my p orbitals are combining together and 1 of my s orbitals is undergoing hybridization. So this also means that I'm going to be forming 4 new orbitals. So that means that once I combine these together, this would make 4 of the new orbitals. So I'll place my electrons in here. So this is sp3, this is sp3, this is sp3, this is sp3, and these all are 4 in number. So the number of orbitals you combine together are equal to the number of orbitals you're producing. Next step would be to make our shapes. Oxygen is in the middle, and then have this here, this, and this. I'm making 4 of these because I'm using 4 of my orbitals here. Now I'll have hydrogen approaching it. I'm not putting this circle, this sphere over here because I just have 2 hydrogens, right? And then also remember that these 2 orbitals have 2 electrons already. So from these 2, they already have 2 electrons. It's already balanced. However, for the other 2, it just has 1, and then hydrogen has the other electrons. And now these are going to combine together. This would look something like this. It's just combining together. So just remember to put the electrons in here. I put electron in a different shade just to show that, oh, you know, your electrons are existing over here. However, well, this is sp3, but the name of this shape would be tetrahedral. But this tetrahedral, if you consider the electron pair geometry. But if you looked at it via molecular geometry, then you need to figure out which are the lone pairs. Molecular geometry. How would you do that? Well, because these 2 were already stable, these 2 already had their 2 electrons, right? So just put them as lone pairs. However, these other 2 are actually making a bond with hydrogen, so they're not lone pairs, they're the bond pairs. So I'll put it here like this. Sorry, this is a bent shape. It's kind of at an angle here. This would be my water, sorry, hydrogen. 2 electrons, 2 electrons. And then these 2 would be my lone pairs. And that is it. So remember, how do I know I have 2 electron pairs? Because these 2 already had their 2 electrons. I didn't need to attach any hydrogen with it to make it have the other electron. It was already stable. It already had 2 electrons. However, for this I needed hydrogen to make it balanced. I needed hydrogen to complete the octet rule, the diplet rule. This is how it has the 2 electrons. So now we'll look at this example and try its hybridization. Well, because these both sides are kind of similar to each other, so we'll just look at one carbon and it would be similar to for the other carbon. So because over here I don't really have a central atom because it's just 2 carbons, so it's technically like this. So I'll just solve it for one carbon, and the other carbon will just follow the same procedure. So for carbon, it's carbon 6. I'll do the electronic configuration. 2p2. This is my valence shell. I'll open it up. 2s, 2px, 2py, 2pz. Now over here, this is my ground state. For this example, I can actually make an excited state. So that would mean that 1 electron from my s orbital is going to go to my 2p z orbital. So we'll have 1 electron left. 1, 2px, 2py, 2pz. Well, over here now, the next step would be to make my shapes. So this is a sphere. The next is the dumbbell shape. So this, I'll put my electrons in. Now the question arises that what hybridization is it going to go under? Is it going to go under sp3, sp2, or sp? Well, in order to know that, we'll look at this carbon over here. Well, if I make it again here, I know that this carbon is making 2 bonds with another carbon here that I don't really need to write for now because I'm just dealing with 1 carbon, and 1 bond with this hydrogen, 1 bond with this hydrogen. So how many sigma bonds do we have here? Well, sigma bonds, we have 1, 2, 3 sigma bonds here. Why not 4? Why is it not making 4 bonds? Why is it 3 sigma bonds? Well, that's because this is 1 sigma bond, so this carbon is making 1 bond with this hydrogen, and the same carbon is making another the first bond with this new hydrogen here. So these are 2 sigma bonds. However, we have a carbon over here, but regardless of that, this carbon is making 2 bonds with another carbon here. So the first bond would be a sigma bond, the second bond is a pi bond. Even if there were 3 bonds over here, so that would mean you have 2 pi bonds. But for this example, you just have 1 sigma bond and 1 pi bond. So in a total of 3 sigma bonds that you're making. And there are no lone pairs, so there are 0 lone pairs. So that's just 3 sigma bonds that you're making. So that means that this would undergo sp2 hybridization. And if you don't know how to figure that out, well, just follow what I do is I put a 1 on top of s, so this would mean 2 plus 1 would mean 3, so I just know that this is 3 bonds. So 3 sigma bonds here. Well, it could also be along with lone pairs, so I just add them up. But over here lone pairs are 0, so it's just 3 plus 0, so I just get 3 bonds. Because it's sp, now that I know it's sp2, I would know that sp2 would mean that I have 2 of my p orbitals and 1 s orbital. So I can just easily use these front 3 over here. So what I'll do is I'll just combine these together now. So because I'm combining 3 orbitals, I'm making 3 new orbitals. So this would result in something like this. But remember, this is not a dumbbell shape. 1 electron here, 1 electron here. And this is 2pz. We'll use it later on, but for now it's just there. Now, because we did it for 1 carbon, the same is gonna get followed for the other carbon. So when I make the shape now, I have 1 carbon here, and it's gonna make this 1 bond, and this carbon is gonna have this other. Let me just put it a little bit on the side. This carbon had its 1 bond, this other carbon had its 1 bond. Well, we can just sort of like overlap them right here. We don't really need to do that again. So this overlaps, so these two get their two bonds, or two electrons, the same carbon, but because these are three orbitals are combined together, so this would have another here and another here. The same goes for this one. So now over here I'll say that, oh, one hydrogen is here, one hydrogen is combined here, the other one is here. I'll put my electrons in here, so one electron, two electrons, two electrons. However, if you notice something is missing, well, that would be my 2pz orbital. What do I do about that? Because if you look at this structure here, I've placed everything. However, I haven't really resorted for the other bond that it's making. It's just one bond that it's making, and this bond that it's making is the sigma bond. But what about the other bond? Well, the other bond is the unhybridized bond that it's gonna have, which is gonna be my 2pz over here. So let me just select another color. So this would be that other bond. So remember, these are not two things. This is just like, this is sort of like together, but I'm just making it like that. But this is like, this is just together as one. So this would be my 2pz, but it's also gonna, this other carbon is also gonna have a 2pz orbital. Now this is gonna make bond parallel in a parallel version. So this is called our pi bond, and that is it. So this is my sigma bond, and then for pi bond, they overlap each other, and it's like parallel. So this is how it kind of looks like. So this is my pi bond. It's just one. Don't get misled with these lines that I made. It's just like showing the bond, but it's just one pi bond that it's making. So this and this, like together, they're just making one pi bond.